All right, so for today's activity, we are going to introduce this concept of a physical map. What you need to do is, as you view this presentation in your notebook, you've got to define the vocabulary terms, the lingo about this topic. You're going to know these terms when they come up because they're going to be red, bold-faced terms. So to get your done stamp, you have to have that list of definitions in your notebook when you're done. First of all, let's talk about what we already know. We got this idea of latitude and longitude, and we know exactly where we are on the planet, and the map scales can help tell us the distance between any 2 points on the planet. But what we're not able to tell at this time is what is it like at that particular location based on the map. We just know where it is and maybe how far it is from someplace else. Let me give you an example of this. Here we've got two places depicted on a map. We see some roads, we see some water, sure, but we can't tell what does it look like? What is the surface of the earth physically like at that location? Well, here's what this location looks like. It's in the plains of Colorado, and you can see it pretty flat. There's absolutely no mountains there at all. Yet the location at the bottom, which looks very similar to the location at the top just from the map, is very, very different. There's some very rugged mountains, some very high points of land, and a low valley. Well, the question then becomes, how do we show the differences in these two locations on a paper map? So how do we do that? Well, there's a couple different ways. First of all, if I draw this, you can kind of see an idea of where the land is high and where the land is low. Versus something like this, you get the sense that, hey, there isn't a whole lot of relief or a change in elevation with the land. And these are the types of maps that we are going to now examine and use. These are called physical maps. Here's your first red bold-faced term. Well, what is a physical map? A physical map is one that shows what a location on the earth is really like, especially if you were really physically there. And with something like this, we got a physical map that can show us that, hey, at point A, you're in the mountains, and at point B, you're on lower ground, flatter ground. And we can tell this by how this map was drawn. You can tell what the land physically looks like if you were standing at that location. Now here we can tell that A and C are both kind of in the mountains, but we can also tell that the mountains at A are much higher mountains than you have at C. So once again, a physical map is any map that shows us what it is physically like at a given location on the planet. Now with this type of map, I can look at the ocean and I can get a sense of where is the ocean deep. Kind of see right here, that's deeper water. And yet right here, we can tell it is more shallow water. So we still get a sense of what the land is like at that particular location. Physically here, the land is down lower, hence you have deeper water. So once again, this is an example of a physical map, but this has a special name. This is called a bathymetric map. A bathymetric map is specifically for the land that's underwater, that land that we can't see. It tells us what the shape of the land is like under the surface. Now, one of the easiest ways to describe the land is the word elevation, which is basically how high the land is. And it's a pretty simple concept. You can see that that's higher up than that. We would say the term higher elevation versus lower elevation. But if we look at this diagram, well, which mountain is taller, A or B? That might depend upon where you're measuring from. If you're in this situation here, looks like B is taller than A. But if you were standing here and you look up at A, oh, that looks higher elevation versus if you were standing here looking at mountain B. We can actually see that this point is higher up, has a higher elevation, but where do we measure from? Because your perspective can't always tell you what's the higher elevation. Elevation has to be measured from some common point, and that common point is sea level, because the oceans are the same all over the planet. Water will even itself out and always have about the same elevation. Doesn't matter if you're on one side of the planet or the other. The ocean is going to be a nice, consistent level from which you can measure elevation. So it's a way that we can all describe elevation and we're all on the same page. We're all measuring from the same point. So when you talk about, well, what mountain is higher than the other? Well, which one is higher up? Which point is higher up from that point that we start measuring? The ocean. So this is handy because the water is the same pretty much all around the planet. So one side of a bowl of water can't be higher than the other. We know that the water is going to level itself out. So this makes sea level a very good point from which to measure elevation so that we're all talking about the same scale. This is a kind of a graphic to kind of give you an idea of what we talk about. Elevation always being measured from sea level. Standing at the beach, well, you're at sea level. You'd be at an elevation of 0. This person is some height or some elevation, some number higher than the sea level. This person going underwater is some elevation below sea level, some actual measurement below whatever the level of the ocean is. Now, on dry ground, you can actually have a point that is lower than sea level. Death Valley in California is very famously a point that is below sea level. And you can see how this works. If you have an area of land that is not connected to the ocean, but it is lower than what the ocean is wherever the ocean is at, you can actually have a negative elevation. And that's described as an elevation that we call below sea level. If you go to Death Valley, you can see the sign there. They have a sign that says 282 feet below sea level. And it's kind of interesting because while you're there, if you're at Badwater Basin, which is the lowest point in North America, you turn around and you look at the cliff behind you, and they actually put up a sign up there to show you where sea level would be. This summer, I went to the Dead Sea, and the Dead Sea is the lowest elevation on the earth below sea level, 435 meters. And you can see the same concept here. Here's the Dead Sea. It's just like Death Valley. Well, here's sea level over here. But the Dead Sea is cut off from the sea, so it's not filled with water, and you can actually have an elevation that is lower than sea level. So another red bold-faced word, what is elevation? It is how high a location is above sea level, or really we could say below sea level. Now, on these physical maps, we need something to tell us some relationship about how high or how low it is compared to sea level. And for this, we need a legend or a key. And on a physical map, it is usually a range of colors that shows us the elevation. And you can see in this map here, the red colors are the highest elevation above sea level. It's going to be over here in these mountains. Florida, which is basically one big beach, everything all at sea level, is going to be that green color. Well, you have to have this. Otherwise, there's no way to get any data from the map. All you see is a bunch of colors. You see general trends, but the legend or the key can actually give you some actual hard numbers that are associated with the different elevations. Now, let's be clear on something here. Notice that these elevations are described as ranges. You don't know an exact number for elevation. All we know is that something in the green is 0 to 250 feet. Well, something here in the yellow is between 1,000 and 2,000 feet. We don't know an exact measurement, but it gives us an idea of the elevation in a particular area. Here's another example of what a legend or a key might look like. It's not just elevation either. It can be other stuff that you would physically see there. What does the land look like? Well, is it grassland? Is it a forest? Is it a desert environment? You're very familiar with this idea that blue on a physical map shows you water. So a physical map, once again, can just show you what it is physically like in an area. But you need this key to describe what you're looking at. Now we'll take these two locations here. Really can't tell what they look like physically in that area. And they're both kind of mountainous. They both have some elevation, but they're very different from one another. This one here is in Death Valley. This here is in North Georgia, and they look very, very different physically. Well, how can we show that on a map? Well, there is a way you can do just that you can describe what does it physically look like if you were there. Something like this. This is a physical map. It shows you the land that is covered by trees. Well, that's what it physically looks like in that area, so that falls in that category of a physical map. And we can see over here, not many trees. Over here, if you were standing there, you would physically see a lot of trees in that location. Now, weather and climate maps are something we're going to look at extensively in this class. And these are actually types of physical maps as well, because they tell you something about what's physically going on in a location. Now, a weather map shows you what the current conditions are. Is it raining? Is it hot? What the temperatures are? Is there cloud cover? Is there a storm there today? This is a physical map because if you were standing at that location, like right there, what would you physically see? You'd see rain coming out of the sky. If you were physically standing right here, what would you see? Well, you'd see blue skies and you'd see sunlight. So once again, weather and climate maps tell you something about what's physically going on, or what is it physically like at a particular location. Now, a climate map's a little bit different than a weather map. A climate map tells you what the weather tends to be like. Not necessarily what it is right here today, but what it tends to be. There's a saying that climate is what you would expect, and weather is what you actually get. Our climate here in Georgia, we know, oh yeah, it's typically kind of falls into that average annual maximum temperature. It doesn't mean it can't be cold. It just means it tends to be in that warmer temperature. But once again, this is a physical map because it tells you what it tends to physically be like in that location. Same thing with rain. Where does it physically tend to rain? This is an example of a climate map. This is not a weather map. It is a climate map because it tells you where it tends to rain, not where it is raining right now today. You can do the same thing with wind. You can do these maps with any kind of physical characteristic of a particular location. Now, there's some key components that maps must have. First of all, we've covered this. You got to have a scale. You got to have some relationship that tells you what number of inches equals what number of miles or feet or kilometers in real life. And they look something like this. Now, a compass, it's got to tell you which way is north, south, east, or west. It looks something like this. And for most of our maps, we hold the map so that north is always pointing up on the page. But we don't have to. So you need this compass to tell you which way is north to help you get your directions or your distance between 2 points. We need a legend or a key which describes, well, what is this map showing us? What do the colors mean? It can also tell us what's the difference between this road and that road. Oh, there's a tunnel in the mountain. There's a railroad track here, not there. What's physically at a particular location. Now, look at some limitations of physical maps, though. This is a physical map. You can see it's got a scale here, and it kind of tells us where is the land low versus where is the land high up. But it's not very exact. We're going to get into this study of what we call topography. Topography, red bold-faced word, is the study of the Earth's surface shape, of which elevation is a big part because the higher or lower it is dictates the shape of the land. A topographic map is one that gives us some more details. It's not just a physical map. It actually gives us some finer details, some numbers. And here's what a topographic map looks like. The difference with a topographic map is that it actually gives us some numbers. We can make some measurements. It's not just a range anymore. It's not just a trend. Here's what a physical map might look like. This is an actual physical map from the United States Geological Survey, and we have these for every location in our country. And you see all these squiggly little lines here. And we can see there's a line right there that has the number 900 on it. Well, this is like a ruler, but it's a ruler going up. That's 900 feet above sea level versus 1,000 feet above sea level. And you can see these lines here. There's 800 feet, and the little lines in between them. It is just like a ruler, except it's going up and measuring elevation. Well, those lines that are like the lines on a ruler that tell us the number have a name. Those are called contour lines. These are drawn on these maps, and they connect points of equal elevation. So if you're right here, you have an elevation of 15. Anywhere on that line, you have an elevation of 15. Well, right here, I'm on the line that has an elevation of 25. And anywhere on that line, I have an elevation of 25. What if you're not on the line? What if I'm right here? Well, I'm not to the line for 15 yet, but I'm past the line for 10. Just like measuring with a ruler, you would estimate. You'd maybe call that elevation 12. Now, it's an estimate, but it's a better guess than just having a range of colors. It gives you a little bit more exactness in the description of the elevation of that point. Now, we can't show a line for every single point on the map. It would just be one huge blob of solid black color where all the lines would merge together. So we only show the lines every so often. You'll pick something like you do on a ruler. Maybe you'll go by 10. Maybe if it's a really big mountain, you would go up by 100. Or maybe you would go up by 5. Just like you can have a ruler that measures numbers in centimeters and then maybe has a line for millimeters or not, these contour lines can be used at whatever interval is appropriate for the land you're trying to measure. Now let's go back to our real topographic map. And you can see that there are numbers on some of the lines, but not on every line, because it would get way too crowded. But if I can see this is my line for 900, and this is my line for 1,000, well, then I've got the lines in between. Just like you have the lines in between on a ruler that measure millimeters that don't have numbers on them, they can be used to make a measurement. But we don't put a number on every single line because it gets too crowded. Well, those lines that do have the numbers are called index contours. And these are lines that show an actual number for elevation. They're usually drawn darker and heavier than the regular contour lines, and they're usually every fifth. So if you look at right there, if I'm on that line, I have an elevation of 700. If I'm on this line right here, I have a map elevation of 800. Well, go up to that line, that line, that line. Well, what do each one of those lines mean? They don't have numbers on there. But if I know that this line is 700 and this line is 800, and there's 1, 2, 3, 4, there's 5 sections to go from 700 to 800, that means each section must be going up by 20. So this would be a 720, 740, 760, 780 line, and finally up to 800. And you can see why we don't write numbers on each line, because it would get too crazy and too crowded. But we have to be able to interpret what the lines in between the index contours mean. We also got to have these index contours, because if I didn't have this line here and this line here with a number, I really wouldn't be able to tell what any elevations values are. So what I just described to you was the contour interval. The contour interval is like a scale that tells us what does it mean going from that line to that line. And I just did it for this particular example. The contour interval for this particular line was 20, because every time we went from one line to the next, we went up 20 and elevation. So the contour interval is like a scale, but it's the scale going up, not across the paper. Now, how do we determine this? Well, this is a process, and you're going to have to do this because there isn't a number on every single line. Well, first thing you got to count is how much elevation is there between the index contours? Well, what's the difference between these two? That's a difference of 100. And then we have to divide that by the number of steps up, or the number of times you go up in elevation. Well, it's going up 1, 2, 3, 4, 5. Well, I've increased by 100. I did it 5 different times, so 100 divided by 5 would give me a contour interval of 20. Something like this. This is how you are going to have to determine the contour interval of the map, because there are not numbers on each line. And these values can change, but the process still stays the same. Now, what can we tell from the pattern of these contour lines? Well, there's a couple things we can tell. Here, we don't see a step up in elevation from 10 to 15. I'm kind of between two lines. Everything in here has about the same elevation because there isn't a new number there. Well, that means the land is kind of flat. You're not stepping up so much. But look over here. Here, as you go walking on that path, physically, you're going up a lot of steps. So you're increasing in elevation. So that means where contour lines are far apart, the land is not changing elevation. It's pretty flat. So think about it. If you were to walk this way, you only step up over one line. You walk a long distance and you only step up once. Over here, however, you go walking there, well, you're not walking a very big distance and you've stepped up like 4 or 5 times. You're going up a lot more than you did in the red circle. Well, that means the land is steep because the elevation is changing a lot versus flat where it's not changing much. And that leads us into our term called gradient. Now, let's set this up. What do these 3 red points have in common? Well, they're all 1,000 feet up. But is there a difference in how you get to each of those points? Imagine you're walking to those red stars. Well, if you go up 1 and 2, if you went up this way and this way, it's the same on either side, right? It's pretty steep. We would say they have the same gradient. Now, route 3, if I walk up this way to get to the top, well, my gradient, my steepness changes. It's steep here. It's kind of flat right there, and then it's steep there again. So my gradient changes. The steepness of the land changes as I walk along that path. But 4 versus 3. Well, we wind up at the same point, but 4 does it on a very steep path. Whereas 3 has some changes in its gradient. Now 5, imagine walking up 5. You still get to 1,000 feet, but it's not very steep. And if you went up 6, you're like rock climbing. That is the steepest or straight up grade. So this is the term called gradient. And this is a red bold-faced word. It's also called grade or slope. This is how much does the elevation, the height, the going up part, change compared to how far you go forward. Basically, this is how steep the land is. And it's very similar to slope in math. We use those terms kind of interchangeably. We also use these terms. A shallow grade means the land is flat. A steep grade means the land is just that. It's steep. You think about hills. And you'll see these signs warning about a steep grade. It means that the land is so steep it can be unsafe, especially for large trucks. An 18% grade is a really steep hill, and if you drive a truck, you got to be careful going down it because you might get going so fast that you'd have a hard time stopping the truck. This is in San Francisco. This is Filbert Street. This is the steepest street in San Francisco. San Francisco is very well known for having very steep streets. And you can see how steep this hill is. I take the same picture and I turn it so that it's level, and that kind of gives you a neat perspective about how steep the land is here. The world's steepest street is in Dunedin, New Zealand. It's a 35% grade, and you can see how steep this land is. It goes up a lot for how far it is going forward. There's another picture where you turn the street sideways and you get a good perspective of how steep the land really is. Now, the steepest street in the US says it has a 37% grade, which seems a little bit more than 35%, but there's only a very small section of this street has that actual grade. It's Canton Avenue in Pittsburgh. It's really steep. Pittsburgh is a place where they get snow and ice in the wintertime. Can you imagine going up and down this street when it's covered in snow and ice? They actually close this street when it snows because it's so steep that it makes it dangerous to go up and down. They do run a little bicycle race on it every year, just for these bicyclists to kind of struggle going up and down, or sorry, going up such a steep grade. Have you ever been to Lookout Mountain near Chattanooga, going to Ruby Falls? That has a 72.9% grade. It is really, really steep. It goes up a lot for all the distance that it goes forward. The steepest mode of transportation that I know of is the Royal Gorge Incline Railway, which is a 45-degree angle. For every foot it goes up, it basically goes a foot forward. And that's really, really steep. That would be a 100% grade. Well, so we're doing some math here. The formula for calculating gradient is as follows. It's very similar to slope in math. To get the percent grade, you take the distance going up, the rise, over the run. And in the physical Earth systems mapping sense, we don't call it slope, we call this the grade. Now you can change the gradient of a path. In some cases, the land's too steep, I can't go up that mountain, especially in cars. The maximum road grade for any kind of decently, not a driveway, but like a street, and a highway is about 8%. Now, for a slope, like in your neighborhood, your roads and your driveways, they can have a higher gradient. But what do? You're building a highway and the hill is too steep, and you still got to get to the top. Well, think about the formula. You can make the grade smaller by doing one of two things. You can either make the distance going forward bigger. If you make that bigger, well, this overall number is going to go down, make the road safer. Or if you make the height less, that would do the same thing. That would make the grade lower and make the road safer. Think about this street in San Francisco. This is very famous, the crookedest street in the country. You notice how it doesn't go straight down the hill. They made the road longer by making it curve back and forth. Well, by making it longer, it decreased the grade. The height stayed the same, but the distance going forward was now bigger, so the gradient is less. And this is very common in the mountains, where you'll see roads do something like this as opposed to going straight up the mountain. By going straight up the mountain, the road would be too steep. But if you go back and forth, you increase the length, height stays the same, the gradient's now less, the road is safer. Hiking paths are the same thing. Instead of trying to go straight up a cliff, you can go back and forth. It's still the same height, but by making it longer, you decrease the gradient, make it easier and safer to walk on. Same concept here with this ramp out of a parking garage. You needed to get cars up to the top. Well, you couldn't make a straight line ramp because it'd be too steep. So what do is you make the ramp go back and forth. You still get to the same height, but now you've increased the length, so the gradient is going to be lower to a safer number. This is why driveways, even in our area, they don't go straight to the house if it's a fairly steep piece of property. They'll do something like this. They'll curve. Sometimes they curve a couple of times. And what this does is it increases the distance going forward to the same height and will make the gradient lower so that the driveway is safe enough or easy enough for a car to travel up. Now here's a case where instead of increasing the length, they changed the height. Instead of making the road go all the way up to here, they cut into the mountain and now they made the height this high. Well, you lower the height, that's going to change the grade. And it made the grade low enough where it's now safe enough to drive. Well, here's a case where they couldn't do either. They didn't have the ability to go back and forth. They couldn't add any distance to the road. They couldn't bring the mountain down. So they had to drill a tunnel to go straight through the mountain because the gradient would have been too great. Now the profile. The profile is what it looks like from the side. And it's one way that you can just kind of look at something and get an idea of the gradient. Can't necessarily do the math, but you can look at something and see, hey, it's steep on this side or the other. For example, here, consider this side versus this side. This side over here is steep. This is a lot more shallower grade. And I can tell this by looking at it from the side. If I was looking from up above, it would be difficult for me to see how the land is shaped and get a sense of the gradient. You build what's called an elevation profile. An elevation profile shows you how is the elevation changing versus the distance going forward, which is what the gradient is. It's how much are you going up versus how much you are going forward. And you can see this is an idea that, well, down here, it's kind of going up about the same, and then all of a sudden it seems to go up really steep. This is for a hiking trail in Yosemite National Park. Here's another one. You can get a sense of what does this trail look like. Well, here you're going up, going up, going up. But in this section right here in the middle, it seems to level off a little bit before it starts to go up and up again. And then it seems at the top it goes up a lot in a very short distance. Well, let's look at this 5-kilometer distance. We can kind of tell, well, what does it look like in this section of this trail? Well, here's what it looks like. It doesn't look particularly mountainous. It's fairly flat. But we can tell at this section, it's really, really steep. It's going up a lot in a very short distance. And that's what it looks like at that point. You can get a sense of what the land is actually like, what the path is actually like by looking at the elevation profile. So the whole point of an elevation profile is it can tell you how much the elevation changes and how it is changing. For example, here, that side, very steep. This side, not as steep. That's the advantage of a profile, a side view. So here are the vocabulary terms you should have gotten into your notebook. If you don't have any one of these, you should kind of back up a little bit, check with your neighbors, compare definitions to make sure everybody's got the right idea. Now, you need to copy these 5 questions into your notebook. These are ideas, concepts. that I expect you to be able to answer. To get your done stamp for today, you've got to show me your vocabulary list, and you've got to show me that you understand the answers to these questions. I'll put a done stamp in your notebook, and that'll be the completion of today's activity.